In this project, the model will be developed to predict the electrical power output of a combined power plant. We have a data set of almost hourly average values for a sensor in the power plant, which we will use in our model. The columns in the data consists of hourly average environmental variables, temperature T, ambient pressure AP, relative humidity RH, exhaust vacuum V, and hourly net electrical power output PE, which is the target we aim to predict. The output metric of our model is a R-squared value of 0.9 or higher. This means that at least 90% of the variance in the target data can be explained by the model. Since the goal is to predict the electrical power output, a numerical target variable based on 4 numerical input variables, the model will perform a regression using supervised learning. When selecting the algorithms, it is important to determine whether the relationship between input and output is already known. Since this is not known, an unparametric algorithm will be applied. Given that we have 4 input parameters and the relationship between them is not known, we need to apply a complex algorithm. For this, the random forest model is particularly well suited. Random forest is an ensemble learning method that trains and combines many decision trees. By combining the predictions of many trees, random forest can also reduce the risk of overfitting, which is especially useful when the relationship between the variables is unclear. As the regression error metric, we use the mean squared error MSE. This should be less than or equal to 30. This means that in our model, an output deviation of up to 30 megawatts would be possible. Since the average consumption per hour according to our data set is 450 megawatts per hour, we are talking about a deviation of maximum of 7%, which is an acceptable size of our case. For training the model, I use Vertex AI, Google Cloud's managed machine learning platform. After setting up the notebook environment, I upload the dataset in CSV format to Google Cloud Storage. Using the Python Jupyter notebook in Vertex AI Workbench, I first check whether the data is correctly stored in the project. Next, I load the data from BigQuery to use it for modeling. As you can see, the code output shows correct number of rows and data structure. Now I split my data for the variation set. Since the simple splitting of the data into training validation and test sets can lead to inaccurate results in a random forest model, k-fold cross-validation is used. The training data is divided into k equally sized parts, so the model is trained k times. 20% of the data will be used as test data. Remaining 80% will be used to train and cross-validation. After starting the training of the random forest and displaying the R-squared score, the MSE metric, and the feature importance chart, we can conduct a clear analysis of the results. Our output shows an MSE value of 12. The R-squared score is 0.96, which proves that the model is very powerful. The feature importance bar chart shows that the ambient temperature AT accounts for about 90% of the model's predictive power. On the other hand, the remaining features have an insignificant impact on the prediction of the electrical power output. To confirm this interpretation, we can train a linear regression model using only the AT feature. Here again, we output the R-squared score, the MSE metric, and the corresponding chart. The result shows an R-squared score of 0.9 and an MSE value of 30. Both values are worse than our tree model, but still within the range of our target output metric. Finally, to directly compare both models via cross-validation, we run command and output a linear regression chart that displays the values of both models. What we can clearly see is that the random forest model has less variance from the regression line. Therefore, the random forest model is ultimately more powerful compared to linear regression. Looking at our output metric again, we can see that the random forest model with a R-squared score of 0.95 and an MSE value of 12 has high performance in predicting the net electrical power output.